Math 2414, volumes. Volume of a solid of revolution, the disk method, example 1. A lot of the problems that we're going to find the volumes for involve taking a lamina and rotating it around an axis to create a solid. If you think about it, there are a lot of objects that can be formed this way. I've got one right over here, one second. It's a bottle of lemon lime sparkling water. But if you can visualize this as a solid, I know the water's going back and forth. If you visualize this as a solid, then you can take a flat piece and spin it around and around to make this. This is actually how a lot of objects are created, or visualized, if you will, by taking a lamina and rotating it around an axis of symmetry. Anything with rotational symmetry can be formed that way, any solid with rotational symmetry. For this one, we're going to take the lamina bounded by y equals the square root of x on top and bounded by the x-axis on below, going from 0 to 4. And we're going to rotate this around the x-axis. The way I usually indicate the rotation is to draw a little circular arrow going around the axis of rotation. So what would this look like if we spun it around? It kind of looked like a bullet, but to get a visual for it, let's see what would happen if we were to take, actually, let's get right to what we need. We need this area function. We need to know what the area of a cross-section looks like if we spin this around. So if we were to spin this around, we'll put another copy of it down here so that it kind of looks like a bullet. And here comes the rotational aspect of it. We need to know if we go over to some number on the x-axis, which we're just calling x to be generic, and we were to take this little bitty slice and spin it around, what shape would we get? Well, it's pretty easy. If you have a lamina that is adjacent to its axis of rotation, another way of saying it is, if you have a lamina where the axis of rotation is one of its boundaries, in this case the x-axis is one of its boundaries, and you rotate it, that cross-section will always be a circle. It's kind of like taking, if you can imagine this being like on a record player and spinning it around, it would trace out a circle. Not doing a very good job of it right now. So we're going to get a circle. Well, that's good because circles are easy. The area of a circle is pi r squared. But how are we going to figure out what that is? Area of the circle is pi r squared. Well, let's kind of play the same game that we played in the last video, where we label the part that we want to know, which is the radius. So we'll put a little r here. Don't need to use a big R because a little r hasn't been spoken for yet. And let's see if we can figure out a relationship between what we know we cut it at x, and what we want to know how tall that is. Oh, wait a second. Isn't this point right here above x, isn't the coordinates of that point x comma r? Yeah, it's over x up r. Is that convenient? Well, only if I have an equation that relates the two. But that point above the x-axis on this curve, where basically the y-coordinate dictates the radius, that point is on the graph of y equals the square root of x. So if I were to substitute this would appear into this equation, the x-coordinate is the same, but the y-coordinate is r. So we would have r equals the square root of x, which is exactly what we need. We want the area in terms of x, and right now it's in terms of the radius. But because the point x comma r is on this graph, whose equation is y equals the square root of x, we can just substitute r for the y, x for the x, and it looks like this. Gives us exactly what we need. We can put that up there. Our radius is the square root of x squared. And at this point you might be thinking, well, yeah, because our radius was just the y-coordinate of this point, and on this graph y equals the square root of x. This sounds like something we can generalize. Well, let's finish this problem first. The square root kills the square, and we have pi times x. Oh, that's going to be an easy one to integrate. Therefore, our volume is going to be the integral, left to right, 0 to 4, of the area of the cross section. Remember, that means if I cut this and show you where I cut it, it will make a circle. That will be its area based on the x coordinate that I cut it at. The volume is the integral of the area. This one's easy. Pi is a constant, and so we have 1/2 pi x squared as our antiderivative from 0 to 4. The 0 annihilates the antiderivative, so being the lower limit, we can ignore it. The 4 does not. 1/2 pi times 4 squared. 4 squared is 16, half of 16 is 8. Our volume is 8 pi. I need to back up for a second. Don't just automatically ignore zeros here. There are some antiderivatives where you substitute 0 and you get something besides 0. You have to follow through there. So that really wasn't that bad once we figured out that the cross section was a circle, and once we figured out that the radius was essentially our function. So maybe there's a generalization here. There's no maybe, there is a generalization. And this generalization is called the disk method. And it goes something like this. If the lamina bounded above by y equals f of x and below by the x-axis over the interval bracket A comma B bracket. I haven't even finished the first part yet. If the lamina bounded above by a function and below by the x-axis over the interval A to B. So something above it, the bottom is the x-axis, and it goes from one number to another. If that lamina, we'll put a comma there, bounded above and below over that interval comma, is rotated around the x-axis, comma, then its volume is v equals the integral from a to b of pi times the square of the function dx. Because each cross section is just a circle. It's called the disk method because if we started with the Riemann sum approach, we would draw a representative rectangle here, a real skinny rectangle whose width would be delta x, and we would take that rectangle and spin it around the x-axis, and that would create a disk. All right, so we have a pretty quick way to handle this, but make sure you understand all the necessary hypotheses. Your function has to be on the top. The x-axis has to be on the bottom, and it goes around the x-axis. This would actually work, though, if your function was on the bottom and the x-axis was on the top. So in other words, if we look down here instead of up here and spun it around, it would just be the negative of that function, but since it's getting squared, the negative would disappear anyway. So that's a pretty handy method. If we're rotating a lamina that is bounded below by the x-axis around the x-axis, then we just have to integrate from a to b pi times the square of the function, and that will give us the volume of that solid.